Thanks, Francis. My name is Natalie, as Francis said, and I'm a hydrologist with Wright Water Engineers in Denver, Colorado, so thanks for having me. And I'll be speaking about rainfall as the driver of post-wildfire flooding and debris flows. So this is a review and synthesis. This is a paper that we recently submitted. It's in review, and I acknowledge my co-authors, Brian Ebel and John Moody with the USGS, so they've been partaking in this effort with me. So this started a couple years ago. I approached John Moody and I said, let's update your 2013 paper, Current Research Issues Related to Post-Wildfire Runoff and Erosion Processes. And this was a well-known paper, at least I looked at it a lot when I was doing my graduate work, just to drive what am I looking at and what are the problems that the research community are saying need to be addressed. And John and authors prepared this paper in preparation for an AGU Chapman conference. Actually, it was a special topics conference, and it was right before the 2013 September floods in Colorado. I live in Colorado, like I said. And they said, let's figure out what the gaps are in process-based understanding and theory of post-wildfire hydrologic response, and then describe how addressing those gaps could improve post-fire hydrologic modeling. So their focus was hydrologic modeling, and that's going to be the focus of my talk today. So a little more detail than we've gotten from some of the past talks over the last couple days. So put your modeling hat on. And John and authors, they went through precipitation all the way through the hazards cascade to soil and sediment erosion and transport, identifying gaps and how addressing those gaps could help modeling efforts. So a decade later, Brian, John, and I set out to synthesize the information that's been published over the last decade and try to fill the gaps that John and authors identified in 2013. And the volume of material that we were producing when we tried to synthesize information to fill those gaps was so voluminous that we said, let's just focus on precipitation for now. So that's why I'm talking to you about rainfall. We're just going to talk about precipitation in our first paper and then try to fill the rest of the gaps in the other kind of hazard cascade processes in subsequent papers. So the gaps that John and authors identified in 2013 related to rainfall representation in models, and I know these words are small, but just to summarize, they called for the establishment of a physical basis for quantifying rainfall at time scales determined by the spatial scale of interest. So let your study area and your study design drive the temporal time step of, let's say, for rainfall forcing that you're using in your model. For number two, they said, let's identify which metrics best represent within storm temporal changes and storm sequence patterns. And metrics are great. Metrics are easily, they can be rules of thumb for what's happening with different attributes of rainfall that we need to account for in our hydrologic models. So I'll talk about metrics briefly today. Number three, they said, let's determine how topography affects the spatial distribution of mesoscale rainfall. And critically, they said, how does topography drive what's called genesis zones of rainfall? And we define that as hot spots of high intensity rainfall. And I'll talk to you about that again today. And then similar, how does topography help control the footprint of a storm that's impacting your study area? Finally, they said, let's account for mesoscale variability within climate structures. It's not just there's a rain event here and it's raining and it's we have constant intensity rainfall. There's a lot of variability with embedded different types of rainfall bands in your synoptic scale structures. So how does accounting for that help us better predict rapid post-fire runoff responses? So those are the major goals. And then last year, Brian Ebel published a paper that was solely focused on modeling post-wildfire hydrologic response. So he wanted to provide a critical review of several dozen papers that were using different physically based distributed model simulation techniques for post-fire hazard response. And he said, how are researchers parameterizing these models? How are they forcing rainfall, et cetera? So it's a really nice review, especially if you're just getting into the modeling realm. And he found relevant to precipitation forcing that 56% of studies again, the studies that he sampled, there were several dozen, used rain gauge measurements for precipitation forcing. And that certainly belies then the importance of getting our rain gauge network correct if so many of our studies are using observations from rain gauges. Another 27% of studies in Brian's review paper used design storms to represent rainfall, and that's really important for me. And I'm an engineer. I work at a private engineering firm. We're oftentimes using design storms to plan for the future. So what are the consequences of the type of design storm that you choose on modeled peak runoff rates and volumes, and I'll talk about that today again. And then lastly, 10% of studies use spatially distributed rainfall data, 8% gridded like PRISM, and then 2% radar estimated. And the last 7%, I don't summarize for you here, but 7% of studies were using something else other than what we have here, like constant intensity precipitation. So the last background thing I want to mention is that Brian looked at the number of modeled sites, and this is really similar to what Paul Santi was showing yesterday, how much research is being done in the post-wildfire realm. And the big takeaway here is that there's been an order of magnitude increase in publications using post-fire hydrologic modeling over the last 2 decades. So let's keep that in mind. I bet everyone in this room at some point is dipping their toe into some aspect of modeling. So it's out there, it's important. We base a lot of decisions on modeled outcomes. And then where in the world is modeling being conducted in studies? Mostly in the Western United States, Mediterranean fire-prone countries like Portugal, Spain, Italy, and Australia. So for Brian, John, and I's review and an agenda for the rest of my presentation, we were grouping our findings, again, to gap fill those areas that I mentioned a few minutes ago, into 4 big buckets. And that's how rain varies temporally. So I'm going to talk about that today. The spatially varying attributes of rain, rainfall intensity, duration, frequency, or also depth, duration, frequency relations, and then rainfall regimes. So to set the stage, I want to talk about some concepts related to rainfall that I want you to keep in mind today during the rest of my slides, but also when you get back to your desks and are carrying out your own modeling efforts. And the question asked is, can post-fire hazard models better account for the following? And I'll illustrate these points. And again, these are kind of attributes of rainfall with this case study up here that I know you can't see well. But this figure first appeared in Moody 2012. That was a USGS publication. And this is showing a storm, a June 2nd, 2001 storm over Rendia Canyon. So this is the 2000 Cerro Grande fire in New Mexico, close to Los Alamos National Laboratory. And what you're seeing are subbasins. Those are the gray dashed lines. So we had a network of subbasins and then a network of rain gauges installed on the landscape. And those are the black dots. And isohyets, those are the red lines that are delineating the peak 30-minute intensity. So you get the recurrence interval, the peak 30-minute intensity. And 4 of those black dots have green circles around them. And the rainfall profiles, or I should say the hyetographs of those 4 rain gauges are plotted on the right. So you can see that there's some temporal variability certainly in what's happening with rain over time. So the first thing to keep in mind is that rain varies in space and time. If you look at those red lines, you can see that the 30-minute peak intensity, this is for again a storm in June 2001, ranged from a 2-year to a 100-year recurrence interval. So that's an order of magnitude, actually 2 orders of magnitude difference. And if you only had a few rain gauges out there, then you certainly would not have captured that spatial variability in rainfall. And then temporal variability is illustrated with the plot on the right. So depending on where you were in the landscape and what time you were looking at the sky, we had major variability in peak rainfall intensity. We're showing 5-minute rainfall intensity in that plot. And then I also just want to point out the green text. I know it's hard for you to see, but that is an estimation of storm advection velocity. So not only was the storm moving, and certainly aspects of topography were driving different types of rain to fall, but also just the pace of the storm as it propagated across the landscape varied from 4 kilometers an hour to over 13 kilometers an hour. So rain varies in space and time. And then there's also this concept of rainfall acceleration. And rainfall acceleration is the slope of a rainfall intensity profile or rainfall profile anywhere along the profile. So typically, if you're talking about rainfall acceleration, and that's the speed at which you're approaching peak rainfall intensity, then you want to talk about the steepest part of your slope. But the main thing I want to point out here is that if you're integrating and you're calculating a slope, then it's fully dependent on what is the time scale or the time step that you're calculating that duration over, and of course where in the storm are you calculating that rainfall acceleration. So the concept of acceleration will pop up again in a few minutes, but the point here is that it's super dependent and requires best engineering judgment on, hey, what is the right window to calculate rainfall acceleration over. Rainfall bursts, these are defined as minor peaks on your rainfall intensity profile. And the point is, rain varies quite a bit throughout the duration of most storms, most natural storms. So you often have blips along your hyetograph, and it's not just peak intensity that matters for runoff processes. It's also what's your soil moisture content as you approach that peak rainfall intensity, and that can be controlled by quick blips or rainfall bursts prior to your peak rainfall. And then lastly, rainfall intermittency. So rainfall intermittency are brief periods of no rain, and that can be defined as no rain or low intensity rainfall within the same storm or between separate storm events. And the point that I want to make with rainfall intermittency is that when it stops raining, if there's a sufficient duration of no or low rain, then you can have the opportunity to recover some of your infiltration processes, other sources of loss. So if you're completely ignoring that recovery period, then you may be overestimating runoff production once it starts raining again. So the first set of findings that I want to talk through are related to time varying rainfall. And the point that I'll make here is that the selection of design storm matters. So what I'm showing here are rainfall profiles, and rainfall profiles differ from rainfall intensity profiles because they normalize for total storm depth on the y-axis. You have cumulative rainfall over total rainfall. So you can plot storms of different depths on the same plot and look at them. And then same with storm duration. You are dividing lapse time over total time. So this is a rainfall intensity profile, and I have 3 real storms on this plot. Those are the colored lines. So the green line is a storm that fell on June 19th through 20th in 2011, and this was over the 2010 4 Mile Canyon burn scar in Colorado. So again, a lot of Colorado examples because I fare from Colorado, as do one of my co-authors. So this storm was a 5-hour storm, and it was classified as a frontal storm. It had fairly low intensities, and it was pretty long in duration for a Colorado Front Range storm. The second storm is this blue line, and this fell over the same exact burn scar. So this is also 4 Mile Canyon burn scar. It was 1.3 hours, way shorter. It was 3 weeks later, classified as a convective storm. And then the red line is the infamous narrow cold frontal rain band embedded in an atmospheric river that hit Montecito in the wee hours of January 9th, 2018, which I know so many of us have worked on that storm. And you can see the shape of that red line is really variable. There's 3 distinct bursts of precipitation. And then of course that was a whole atmospheric river was impacting that system, so the actual duration of that storm was quite long. So the other lines plotted on here are design storms, and I just selected some of the really commonly used design storms, the now antiquated NRCS Type 1, Type 1A, and Type 2 storms are some of those black dashed lines. The NOAA Huff probability or distributions that you can grab from the NOAA temporal distributions right off their website. And the first point I want to make is that real storms do not behave like smooth design storms. So as a hydrologic engineer or physical scientist, you're also choosing design storms, and you just have to pick the best storm that captures the attributes for the catalog of storm types that impact your study area. But again, real storms don't behave like smooth design storms. That NCFR had 3 rapid bursts. There is no design storm that looks like that storm. Second, the selection of design storm has major consequences on modeled peak discharges and total runoff volumes. So I'll illustrate this point with the NOAA Huff distribution. And back in 1957, a man named Huff said, hey, if we just figure out what quartile in the total storm duration the majority of your depth or volume of rainfall occurs, then we can break out by probabilities, and you can choose design storms that put the majority of your rainfall in the 1st, 2nd, 3rd, or 4th quartile. And I'll just illustrate the point of why choosing the wrong quartile might really get you some incorrect estimates of total peak runoff. Let's say you choose that yellow line that I highlighted here. So this is a NOAA Huff distribution for the 1st quartile storm. So the majority of the rainfall happens in the first 25% of the duration of the storm. And that means that in this model application, some of your peak rainfall intensity will be consumed by initial abstraction, right? So not all of your peak rainfall intensity will be translated into runoff or will be effective rainfall. But in reality, if in your area, the types of storms that impact your study watersheds put the majority of the rainfall in the second or third quartile, then that means that by the time high intensity rainfall occurs in reality on your landscape, all of that might be effective runoff. So if you're using a first quartile NOAA-Huff distribution in an area where most of your rainfall happens later in the storm, then you're likely going to underpredict both peaks and possibly totals. The design storm selection should depend on your study objectives. So if you really care about, let's say you're not doing post-fire debris flow work, but you're thinking about water supply from a longer term perspective, then maybe what you really care about is yield. So you need to pick a design storm that gets the totals right? It maybe doesn't matter so much about the peak rainfall intensity, but let's make sure you get totals right. But if you're doing post-fire debris flow hazard work and you're thinking about rainfall triggering thresholds or flash flooding thresholds, make sure that your design storm at least gets the timing and the depth of your peak rainfall intensity, because what we really care about is that short high intensity rainfall. And then lastly, constant intensity rainfall has been shown to underpredict peaks and totals across the board. And that's just that 1-to-1 black line that I put on here. And I only put that on here because every once in a while I still run across a study that uses constant intensity rainfall, and just nowhere in the world does constant intensity rainfall happen for a real storm. So you better have a good reason if that's how you're parameterizing your model. Time varying rainfall, the second topic are rainfall bursts. So we already talked about those. Those are minor peaks on the rainfall profile. And what I'm showing you here is another rainfall intensity profile. So we have a hyetograph on here, and this is, again, the June 19th through 20th, 2011 storm that we already talked about. It impacted 4-mile burn scar in Colorado. So what we did is we tried to model what actually happened with that rainfall, which would be the blue line. There's a lot of variability over time, even though that was classified as a frontal storm. And if you, in your landscape, said, okay, let's install equal time interval sampling rain gauge instruments. Those would be instruments that report out rain every 30 minutes, like cumulative depth of it every 30 minutes, or some discrete time interval. But this example is for a 30-minute rain instrument, or also if you're using 30-minute gridded precipitation data, for example, then the best hyetograph you could get to emulate this storm would be the black line. So you're not resolving peaks and troughs very well with this equal time interval sampling method. Perhaps a better instrument type to put out in your landscape if you really care about high intensity rainfall, so peaks and troughs in your hyetograph, would be equal depth interval or tipping bucket rain gauges. So for example, if you had a 1 millimeter tipping bucket out in this landscape and you were trying to sample this blue line storm, then you get a lot better at resolving that variability. That red line is at least getting a lot closer to the rainfall peaks. And certainly for smaller volumes, so less than 1 millimeter, you resolve those peaks and troughs even better. When it's raining hard, then your tipping bucket is dumping more quickly or more frequently. Rainfall intermittency, again, periods of no rain or no rain both between storms of different distinct events or within the same storm. The importance of rainfall intermittency on runoff production became apparent as the resolution of instruments, well, really the data that's backed out from instruments increased. And the point that, again, I want to make here is that intermittency can affect runoff response when the duration of that intermittent rainfall is sufficient to allow for recovery of infiltration and other sources of loss. So I'm not summarizing metrics for burstiness or intermittency, but our paper certainly does. There's several metrics out there that you can run your rainfall data through and say, do I have a regime that is known for higher intermittency or burstiness? And then you compare regimes based on the metrics that you back out. So we provide that information in this paper. Spatially varying rainfall, we'll talk about the spatial scale of storms real quick. The table on the left is summarizing the spatial scale, so typical diameters of some of the most common storm types in the western United States that impact burned areas. So we're moving from the synoptic scale or large scale, like extratropical cyclones, warm and cold fronts, including atmospheric rivers, down through the mesoscale, tropical cyclones, narrow cold frontal rain bands embedded within other features, convected cells. And the point I want to make here is that you can do something really helpful for your client or your project sponsor, maybe your agency partner, by looking at gridded rainfall data, let's say historic data, and delineating where are genesis zones, take a storm catalog. This is a plot that was generated on 20 different storms, 20 different days over several years. So this is, I think, MRMS radar data. I didn't put this plot together, but we gave a project partner, this is the Hayman burn scar. So this is the 2002 really infamous burn scar that was important for Denver Water, one of our major water providers on the Front Range of Colorado, because it burned a lot of their source water area. And we said, hey, look at these genesis zones. Put this on your burn severity maps or your USGS debris flow probability hazards. And you can figure out, this is where I'm often gonna see really high intensity rainfall, and those are the pink blobs on there. So not too hard to do. We have the data now with gridded rainfall data that goes back in time of shorter duration than just PRISM daily data. The optimal separation distance is thinking about how, let's say you want to characterize spatial rainfall variability in your study area, and you're asking yourself, well, what is the optimal separation distance that my rain gauges have to be to sample the variability of rainfall that's impacting my area? Or if I'm using gridded rainfall data, what is the sufficient resolution of each grid cell to characterize or again capture that spatial variability? And you can use something called, I'm going to just jump to this, the semi-variogram, which is used to determine that optimal separation distance. So optimal separation distance, again, this can be thought of as distance between your rain gauges or the resolution of your gridded rainfall. That theoretical sampling interval is termed the Nyquist frequency, which is 1/2 d, and that's in the second bullet point. And 1/2 d is the spatial footprint of the storm, so the diameter of the storm. And you can use semi-variograms to capture how the variance of a variable, let's say for this example, rainfall intensity, varies with distance. So on the y-axis is variance in rainfall intensity. And then on the y-axis is separation distance. So on the bottom left of the plot, let's say those are two rain gauges that are really close together because they are not separated by much distance. Then your variability between rainfall would be low. You're sampling really similar rainfall. But as you move out in space and increase your separation distance, then the variability or the variance between rainfall intensity measurements should increase. And at some point that variability will asymptote. You will have no coherence between your rainfall. And that's termed the sill. And that is the point at which you're no longer sampling the same storm event. So semi-variogram is a really good way to figure out what is the optimal separation distance for my rain gauge network. Let's see, 5 minutes, right, Francis? Okay. IDF relations. So scaling properties of rainfall is something that we use to think about how can we redelineate rainfall regimes in the Western US. And for a given frequency of rainfall or recurrence interval, the maximum rainfall intensities are self-similar such that this power law describes maximum rainfall intensities. So I'm going to break that down just for a second. We're looking again at those two frontal and convective storms that impacted the 4 Mile Canyon burn scar. This is on the plot on the right. And these are just typical intensity duration curves. So for different rainfall durations, right, you have decaying maximum peak rainfall intensities, and you can fit a power law to that. And importantly, the exponent on the power law, so you could fit a power law to both of those lines on there. And one of the lines is the convective rainstorm, that's the solid black dots, and then the other line is open dots, and that's the frontal storm. So the power law that describes the decay of peak maximum intensity, which occurs at your shortest duration, is this N decay rate, that's the exponent. And there is certainly precedent for thinking about how to use this decay rate to describe the advective or convective properties of the rainfall regime impacting your study area. So Monjo in 2016 said the fitted exponent of the power function is a dimensionless index that reports on the rainfall concentration over time. And importantly, it gives an indication of the greater convective or advective contribution to the precipitation process. So John and Brian and I said, can we start thinking about, let's look at rainfall intensity, duration, frequency relations all over the western US and start seeing if we can define regimes, convective or advective, i.e. frontal regimes, based on how data plots in the KN space. And all this is in this paper because I know it's hard to see. But the point is, we took NOAA Atlas 14 data, we just chose a few specific sites and fit power law relations to different NOAA Atlas 14 locations, so Colorado, Utah, Arizona, and that was all for the 2-year recurrence interval. And we also did the same for a few storms, so admittedly not 2-year recurrence interval, but those pink plus signs on the top of the plot, those are the narrow cold frontal rain band that impacted Montecito. And in the KN space, the higher up you go, the y-axis is the K value, so peak intensity. So those are indicative of storms with really high peak intensity. But the farther to the right you go, because the x-axis is that N value or decay rate, if you're really far off to the right, that means that you have a really short duration of high intensity rainfall. That is indicative of a convective type storm. You got really high rainfall, you have aggressive convection, and then that decays quickly. If you're in a frontal system, and one of the most important takeaways, I think, because we often think of frontal systems as drizzle, long duration, you can still get high intensity rainfall that just lasts for a longer period of time, and that can be pretty problematic when we're thinking about triggering conditions. So 3 more minutes left. I will have to cut a couple things out, but I think the point I want to make here is we said, can we refine rainfall regime delineations that have been widely used so far in the past, and using this KN framework. So we looked at a couple delineations, and rainfall regimes are efforts made to say, hey, where is the meteorology in a certain area cohesive enough to say that storms have similar mannerisms or characteristics. In 1922, Kendrew delineated rainfall regimes based on air mass analysis. So that is the black dotted lines that you see on the western US here. For example, over Arizona, he said, I'm not going to look at rainfall characteristics. I just know that we have moist sources of air coming up from tropical California, the Gulf of California. And so this is the North American monsoon kind of rainfall regime, etc. He did that for the whole US. And then Moody and Martin in 2009 did something similar with intensity duration relationships. And those are the colored blobs on here, but those are still pretty coarse delineations for rainfall regimes. So I said, you know what, let's take every data point in the NOAA Atlas 14 data set, and let's just not pull out some random locations like I did a couple slides ago, but let's fit an IDF or a power law to every data point in NOAA Atlas 14. So that was several million data points. And then let's delineate rainfall regimes based on their KN values from those power laws. And I'm just going to jump to this plot because basically we fed those KN fit exponents and coefficients through a k-means clustering algorithm and then plotted how those data segmented, and that's the left scatter plot. And I said, let's use 10 clusters because I used an elbow plot. And knowing nothing more than just KN relations, where do those those segmented clusters plot on space? And they do actually plot similarly. I had no geographic information in here, but the point is the highest intensity, shortest duration rainfall, that plotted in the eastern Colorado plains and on the Colorado Plateau. And then you can similarly describe rainfall behavior for all the other regions of the US. And this was it was an arbitrary decision to choose 10 clusters. But in this way, we were able to more discretely define rainfall regimes and explain what that behavior looks like based on the KN space. So I have some key takeaways, and I won't go through them because I'm out of time, but thank you. And I'll take questions during breaks.